In this lesson, we're going to talk about matrices. So what is a matrix? An m by n matrix is a rectangular array of m rows and n columns of real numbers, where m and n are whole numbers. Okay, so it's a rectangular way to organize data. So we've got an example here. So here's matrix A. We use capital letters to stand for matrices. We've got a matrix that has 1, 2, 3 rows and 1, 2 columns. So we call it a 3 by 2 matrix. Okay, and that's the order of the matrix. That's our m by n. That's our dimensions of that matrix, 3 by 2. Okay, each number is an element or an entry. So 0 is an element, 6 is an element, and so on. The element A sub ij is in the ith row and jth column. So what does that mean? Let's look at an example. What is A sub 3, 2? Okay, so what we want to find, we want to find the element that's in the third row and the second column. So if we go 1, 2, third row, and then second column, the intersection of those two is 1/3. So A sub 3, 2 is 1/3. Okay, a couple more terms. A square matrix is when m equals n. Okay, an example, B equals 1, 9, 3, 7. Okay, so it's got the same number of rows as columns. Equal matrices have the same order and their corresponding elements are equal. Okay, so if C equals 1, 9, 3, 7, it's a 2 by 2. B is a 2 by 2. They both have the same order. They both have the same elements in the same spots. So 1, 1, 9, 9, 3, 3, 7, 7. So therefore B equals C. Okay, we can do operations with matrices. There are similarities with the way we do operations with matrices with the way that we do operations with real numbers, but there's also some differences. So let's start off with addition and subtraction. We add or subtract two matrices of the same order by adding or subtracting their corresponding entries. Matrices of different orders cannot be added or subtracted. Okay, so they have different orders, you cannot combine them. And the order of the resulting matrix after you add or subtract two matrices will have the same order as the matrices being added or subtracted. Okay, so let's look at a couple examples. We've got matrix D, matrix E, and matrix F. If we're asked to find D plus E, first off, let's check the order of each one. So D has 2 rows and it has 3 columns. So it's a 2 by 3 matrix. E has 2 rows and 3 columns. So it's also a 2 by 3 matrix. So we can add these together. So the way we do that is we add corresponding entries. So the entry in the first row, first column, plus the entry in the first row, first column of E. So 4 and 1. And if we go across our row, a first row, second column, 1 plus a -1 gives us our second entry, -2 plus 0, and then we do the same thing for the second rows. Okay, and then we simplify each of those, and our resulting matrix is, again, a 2 by 3 order matrix. Okay, if we're asked to do E plus F, again, we want to check our order first. E is a 2 by 3, F is a 2 by 2, therefore they don't have the same order, so we cannot add them. It's impossible to add those two. Subtraction, E minus D. So we want to take this matrix E, subtract matrix D. We've already checked their orders out in the first example. So again, take corresponding elements and subtract. 1 take away 4 gives us -3. -1 take away 1 gives us -2, and so on. Our result is a 2 by 3 matrix, just like what we started off with. Okay, in your notes, you do D minus E and F minus D. Okay, next operation we can do with matrices is called scalar multiplication. Okay, when we work with matrices, real numbers we call scalars. Okay, and we use this lowercase k to represent a scalar. To find the scalar multiple of a matrix, multiply each element in the matrix by the scalar number. The order of the resulting matrix does not change, just like with addition or subtraction. Okay, here's this same explanation of scalar multiplication symbolically. Scalar times matrix. We take the scalar and multiply it by each element. So, example, if G is this matrix, first off, this is a 1, 2, 3 by 2 matrix. They want us to find 4G. Okay, so we're going to do a scalar multiplication. Our resulting matrix should have the same order, 3 by 2. So we're going to take 4, multiply it by our matrix G, and we're just going to distribute that 4 to each of our 6 elements. Simplify, and here's our resulting G. We've got a 3 by 2 matrix. Okay, another vocabulary word is zero matrix. Is a matrix with every element equal to 0. Here's a couple examples. Here's a 1 by 1. Here's a 2 by 5. They can come in any dimensions as long as all of the elements are 0. Okay, if you add a 0 matrix to any other matrix with the same order, then it's not going to change the matrix that you're adding to, just like 5 plus 0 is still 5. Okay, in your notes, you try, if H is this matrix, find 2G, using this G up here, plus 3H. Okay, our next operation, matrix multiplication. So we had scalar multiplication just now. There are opportunities to multiply 2 matrices together. Okay, so to find the product of 2 matrices, A, B, we got to look at these 3 bullet points. Okay, the number of columns in A must equal the number of columns in B. If they don't, we cannot multiply A and B. The order of the resulting matrix is going to be the number of rows of A, the number of columns of B. So notice these are the 2 parts of our dimensions that we did not check in our first part. Okay, each entry of the product is obtained by summing the products of the entries of a row of F by the corresponding entries of a column of B. So let's look at an example. We've got matrix J, we've got matrix K. First thing we want to do is find the order of each of these. J is a 2 by 3 matrix. K is a 3 by 2 matrix. Okay, so we want to check and see if the columns in A, which is our J here, is the same as the number of rows in B, okay, which is our K. So we want to check, are these 2 numbers the same? Okay, and in this case, yes, they are. So we can multiply these 2. The resulting matrix is going to be the 2 numbers that are left. Okay, our result is going to be a 2 by 2 matrix. So it's going to be different dimensions than what we started off with. Okay, so to find JK, when we multiply those, we want to take this first row, multiply it by this first column. So we want to take 2 times 1, add that to 1 times 0, add that to negative 3 times 1. Okay, imagine just taking this row and turning it and multiplying the corresponding numbers and summing up those products. Okay, that gives us the element in the first row, first column, since we multiplied the first row times the first column. Okay, to find the second row, first column, take the second row of numbers, 0, 1, and 2, multiply it by the first column, sum them up. And then to find our second column in our resulting matrix, multiply the first row in J by the second column in K. To find this last element, second row times the second column in K, add up those products, and then just simplify. 2 times 1 is 2, 1 times 0 is 0, negative 3 times 1 is negative 3. Okay, 2 and 0 and -3 makes for -1. And then do the same thing for each element. Again, our result is a 2 by 2 matrix, because those were the number of rows in our first matrix by the number of columns in our second matrix. Okay, next up, identity matrices. An identity matrix, we've got 4 examples here. Our first identity matrix, a 1 by 1, is just the matrix with the element of 1. Identity matrix that's a 2 by 2 has a 1 on the diagonals going from top left to bottom right, and the zeros everywhere else. Identity 3, again, 1s on the diagonal from top left to bottom right, zeros everywhere else. Okay, same for any other square matrix. 1s go along the diagonal from top left to bottom right, zeros fill in the rest of the elements. Okay, for any n by n square matrix A times the identity matrix equals identity matrix times A equals A. So kind of our result of multiplying these two is A, and the result of multiplying them the other way is also A. Commutative property is not always true when we're multiplying matrices like it is with real numbers. All right, let's look at an example. Matrix F. We've got a 2 by 2 matrix. 2 by 2. Okay, we want to prove that this is true with this matrix F here. Okay, so we're going to do Fi on our own, and you're going to try I times F and see what we get. So we start off with our F multiplied by our I, our 2 by 2 identity matrix. Okay, again, row by column to fill in our entries. And when we simplify, we get exactly what we started off with F. Okay, so for this part, so far so good. In your notes, you try with I first and F second and see if you get the same thing. Okay, next up, inverse matrices. For any n by n square matrix A, B is the inverse of A. Okay, here's our notation for inverse of A. If A times B equals B times A, they both equal the identity matrix of the dimensions that we were started off with. Okay, so if you can find 2 matrices that when you multiply them together either way, A times B or B times A, and they both end up with the identity matrix, 1's on the diagonal, 0's everywhere else, then they are inverses of each other. Okay, not all square matrices have inverses. A non-singular matrix is a square matrix with an inverse. Singular is a square matrix that does not have an inverse. Okay, example, prove that L and N are inverse matrices. Okay, we're given L, we're given N. First thing I want to check are my dimensions. I've got a 2 by 2, got another 2 by 2. Okay, so we've got 2 square matrices. So far, so good. So to check to see that they are inverses, we want to multiply. So let's start off with L times N. Row by column, simplify. And we end up with our I2 identity matrix. Okay, so far so good. In your notes, you try NL. See if you come up with the identity matrix. All right, next up, almost there. Determinants of a 2 by 2 matrix. The determinant of some 2 by 2 matrix A, we can write in a couple of different ways. We can write DET of A, or we can write our matrix A with kind of the absolute value or the modulus or the magnitude bars around it. And if our matrix A has elements A, B, C, and D, then we can also put those bars around the actual matrix with the elements in it without the little square parts. Okay, and then finally, to find the determinant, we take A times D, and then we subtract B times C. So we're multiplying the diagonals, and we subtract the products of those two. Okay? An n by n matrix A has an inverse if and only if the determinant does not equal 0. Okay, so let's look at some examples of when we can use this. We're asked, do these matrices have inverses? We've got 4 matrices that we're given, P, Q, R, and S. So let's start off with P. Okay, we've got a 2 by 2 matrix. So let's find the determinant. To find the determinant, we do 3 times 2 minus 1 times 4. So we get 6, take away 4, which is 2. 2 is not 0. Therefore, the inverse of P does exist. So yes, P has an inverse. Okay, we don't know what it is right now, but we know that it exists. Q. Q is also a 2 by 2 matrix, so it's a square matrix. So let's check it. So we've got 6 times 5 minus 3 times 10. 30 take away 30 is 0. 0 does equal 0. That can't happen. So there is no inverse for Q. Inverse of Q does not exist. Next up, R. R is a 2 by 3 matrix. 2 by 3 is not a square matrix. Therefore, inverse doesn't exist. It only goes for square matrices. Okay, try S. See if this matrix has an inverse in your notes. Okay, last board. We're going to look at finding that inverse of a 2 by 2 matrix. All right, if the determinant of A does not equal 0, then the inverse of A, which we can also write with the matrix and its elements, with the -1 exponent, equals 1 over the determinant times, so doing some scalar multiplication here, times, and then notice what happened between here and here to our matrix. Okay, so 1 over the determinant, the reciprocal of the determinant is our scalar. Our matrix, what happens is we take our A and our D, and we switch places. Then we take our C and our B, and we just take the opposite of each of those. Okay, they stay in the same place. We take the opposite of the C, opposite of B. All right, this is going to give us the inverse of a given A matrix, as long as the determinant doesn't equal 0. So, example. Last one. Find the inverse of each matrix. We've got a T matrix and a U matrix. Okay, T is a 2 by 2. It's a square matrix. If we were to find the determinant, 2 times 4 is 8, minus 1 times 3, 8 minus 3 is 5. Okay, so it's a non-singular matrix. So, we take 1 over that determinant, and then we switch places of our 2 and 4, and we take the opposite of our 1 and 3. So 1/5 times that new matrix. So our inverse for T is 4/5, -1/5, -3/5, 2/5. Okay, still a 2 by 2 because our inverses are the same order as our original matrix. Find the inverse of U in your notes. Next class, we will go over these problems that you were doing yourselves. We'll talk about finding the determinants and the inverses of larger square matrices with bigger dimensions than 2 by 2. And we'll look at doing some of these matrices operations in our calculators.